Short plus what I write.
The Henderson Hasselbalch equation. Now, like what I just showed you a second ago, all right, I'm going to show you how to do the same thing, but all in one equation, all right? And it will, it's going to be a long derivation, and I want you to be able to do this on the test. However, once you get that derivation, the actual problem itself will become, like, seriously, less than a minute to do versus doing the ice and all the other stuff, okay? All right, now don't copy what I'm about to write down just yet. All right, I want to just show you something first, okay? Just to remind you quickly, when you have a salt and you have an acid, the common ion effect, forces the equilibrium expression back that way so it's not as acidic, okay? We already know that. But that's not what I want. I want to point something else out to you, too. I want to be able to do this without doing a big, long ice problem, okay? I don't want to have to do that. And I don't, and here's why. Turns out that, if you remember, over here you'd have like in the last problem, 0.20 plus x, right? And over here we had 0.100 minus x. Remember that? Just a minute ago. But we ignored both of those x's. And since we ignored both of those x's, the concentrations were basically whatever they gave me in the problem, 0.2 and 0.1. So I didn't really have to do all of that. All right, and that's going to be the key to this. All right, that's going to be the key to this derivation of the Henderson Hasselbalch equation. The fact that I can ignore the x's and here's the second key. Most of the time, you're going to want, in a buffer solution, the pH. You're mostly going to want the pH. So I'm going to rearrange that whole equation to solve it for pH. And I'm going to take into account the fact that I can ignore x, which makes the problem a really easy problem. Okay, let's do, copy this down here now. Whoops. That's not right. Slowly turns. All right, Henderson Hasselbalch. All right, I do want you to write the equation down again. Write that one. That's a salt. Salt just breaks up in solution, the sodium ions and whatever the negative ion.
That's a salt.
It's a salt. All right. The acid, he breaks up as an equilibrium expression into hydronium and whatever the negative ion is.
This is a very sad chapter. Everybody's breaking up. There's going to be drama next chapter.
Now, I'm going to start from scratch and derive this new equation called the Henderson Hasselbalch equation. In the meantime, as I start this is going to be a great little review because remember, I can ask you any one of 3 derivations. All right. Now, last chapter was totally bonus. This time, it's not. You're going to have one of these. So here's what you would do. And it's the reason I want to do this again. Okay. This would be a nice little review. Matter of fact, Lizzie just asked about it. Did you ever go over the review for Ka, the derivation of Ka? This is exactly what you should have for your derivation of Ka. And then we're going to go beyond that to the Henderson Hasselbalch. Matter of fact, oh, I just realized something. I never corrected. There's a mistake in here. Just for a second here. It should be.
Guys, copy it down quick.
Don't copy.
Holy crap.
Okay. It's long, as you can see. That's what we're going to be copying. But I want to go through it.
Wow. That's
all right. Now, first off, remember, this goes way back to kinetics. If I assume a one-step mechanism, then I know that the rate forward is going to equal the reactants raised to their coefficients. Okay. The rate reverse would be the products going back that way. They be the reactants raised to their coefficients. So it equals Kf times HA times water, and then Kr, hydronium times the negative ion. This is actually from the kinetics chapter. Now, we get to the previous equilibrium chapter, where we learned that at equilibrium, what do we know about those 2 rates? Right. So at equilibrium, the rate forward equals rate reverse. This is from scratch. Everything you would need to do the Ka derivation and beyond, which I'm going to go on past that. Okay. So if the rate forward equals the rate reverse, that means this guy equals that guy. That expression equals that expression. Kf times the reactants equals Kr times the products. Fine. What did I do next? Do you remember?
Divided.
By what? What do I want to do? What's the point of dividing by what? I want to get what to what side?
want to get the
Now I want to get all the constants over to one side, and I want to get the variables to the other. So I divide both sides by KR. That gives me KF over KR, right? And I also have to divide both sides by HA and water to get rid of them on this side, right? So I get that. So everybody understands so far? And you should. This isn't the first time we've seen this. This isn't the second time we've seen this. This is about the third or fourth time we've seen it, because we saw it for KC, we saw it for KW, we saw it for KA, and now we're seeing it for the Henderson Hasselbalch. So this is the fourth time you've seen it. And you had to do it in the homework problem, too, fifth. Now, what do we know KF over KR actually equals then?
KC.
So that is where we left off from chapter 1 on equilibrium, the first chapter on equilibrium. Now, we went further. In this chapter, we realized that since we're dealing with weak acids and dilute solutions, what can I do with that water?
He's a constant.
Yeah, he's a constant too. So I'm going to bring him over to the other side, okay, because water is virtually constant. And basically, you'll get Kc times water equals that. There you go. That's nice. And if this had been the equation for water up here, water times water equals hydronium times hydroxide, I'd be pretty much at Kw right now. As it is, since it's for a weak acid, I'm at Ka. That's what Ka equals. Oops, I didn't mean to do that next one. Yeah. Okay, so that's what Ka equals. So, if I asked you to derive Ka, you would have that much information, and that's what you would do. And with including those little statements, I would like. Bare minimum, that's what you would need. Now, let's go beyond that. I want the Henderson Hasselbalch equation. That equation is going to basically be solving for the pH. All right, because that's what you mostly want for a buffer solution. You want to know what the pH is. So, I want to get hydronium by himself. Because after all, what's pH? Negative log of the hydronium. So, let's rearrange and get hydronium by himself. To do that, look at what I'd have to do. Do you all agree? I want to get hydronium by himself, right? That's my equation right here at this point. So basically, I would multiply both sides by HA over A, correct? Okay. And somebody actually asked, what does the X mean here? What does that mean? Times. Okay. So the Ka times HA over A. I'll go with that. Okay, we're going somewhere with this. What would I want to do next if I want the pH? I would need a negative log, right, of the hydronium. So the negative log of the hydronium, and then a negative log of this. Now I'm not sure if I did that next or the explanation next. Hold on a second. How's the explanation next? Okay. So, all right, I am going to do that, but before I do, let me say this. What makes this problem easy is that these three guys can be determined directly from the problem. When I gave you that problem, I would say it's a 0.10 molar of the acid, 0.20 molar of the salt, and the Ka was 3.5 to 10 to the negative 6. I can plug them in, and here's the reason why. As I hinted at the beginning of this, HA, the acid's concentration, I can ignore X because it's so small. For the salt's concentration, it's just going to be whatever the salt is. I can ignore X. So, in a buffer solution where the concentrations of HA and the salt are at least 0.05, and your exponent for a weak acid is -4, which by definition it has to be a weak acid pretty much, you can use a simplifying assumption, and the HA is going to be whatever the concentration is in the problem, and the A is going to be whatever the concentration of the salt is in the problem. And therefore, it makes it real easy to do. I could just plug those guys right in from the problem. And it would look kind of like this, wouldn't it? You could replace what you have for HA or salt as acid over salt, whatever that concentration it gives you from the problem. And Ka is obviously given to the problem also. It has to be. Okay. So copy all that down. I know that's a lot. We're almost done. Almost. Remember, our goal was not to get hydronium, but to get what? pH. Okay? So we have one more thing to do here. And it's going to look weird to you when I do it. Somebody's going to say, oh, you made a mistake, which I almost did. Previous class, I corrected it, but made a mistake actually at this point. I got ahead of myself. All right, so you know what I'm going to do if I want to get the pH, right? I want to take a negative log of both sides. Well, a negative log of the hydronium, that's easy enough. How do I do the negative log of Ka times the negative log of acid over salt? Watch and see if you can figure out why this makes sense. Copy all that down and see if that makes sense. You got one more. Actually, it doesn't even fit on here. There's one more thing to write, actually. But first, write that down. And let me explain why it looks like that. It looks like I made a mistake, doesn't it? Oh, you made a mistake with the salt and the acid. That's what somebody's going to say. But I didn't. And I'll show you why in a minute. Made a mistake.
Mr. Ron, you made a mistake here.
Thank you. Thanks for noticing. Okay, let me explain to you why this actually is not a mistake. You say, well, you have negative log here, you have negative log there, but then you've got positive log, and you flip salt and acid. Is that okay?
Yeah.
Is that
It's just the
positive?
inverse.
Is that times positive log?
It's not times. All right, let's take Lizzie's first question. Logs are exponents, correct?
Oh.
If I have 10, whoops, oh no, stop! All right, let's take Lizzie's first question. I hadn't thought about this one being a question, but it's a good one. Listen, we're going to get there. Let's take Lizzie's first. Her first question is, she's thinking maybe that's still times because it was times up here. Maybe she thought that was the mistake I was talking about. No. If I have 10 to the 4th times 10 to the 2nd, what do I do with the exponents? You add them. That's why that's plus there. I'm talking about the powers, right? So we do add them. That is a plus because the log is the power to which 10 is raised. So the answer, set 4 and 2 is 6, 10 to the 6. So that's one problem. The other problem, if you haven't figured it out yet, I know some people did, I heard them talking. Why am I allowed to have a positive value here when I had a negative in front of these guys? It should be a negative. And it could have been a negative if I had kept it as acid over salt. But remember, 10 to the negative 2nd power is 1 over 10 to the 2nd power. When I take the negative of the log, negative times the negative is a positive, I can flip those two guys, basically. All right, and it's the same thing. So my final equation is, which I ran out of room on my board, I'll put it up here. Underneath this, what is negative log of hydronium? pH. So pH equals what? The pKa plus the log of the salt over the acid. Wow. Now that is one long derivation. Now, by the way, you might be wondering, why did I put pKa instead of negative log of Ka? What does P mean? It means negative log of. That's basically what it means. That's why it says pH, negative log of hydronium. Wow, that's fun. That is a lot of fun.
I can't wait to do this on a test. I'm gonna get it right.
Yeah, I can see. Now, I don't think I have the homework on the board up here this time, but it's 819. It's right over there. 21A, 23A, and 24A on page 819 for those of you who are not.